Hello, everyone. This is Stephen Massa with the Water Environment Federation. I want to welcome each of you to the Benefits of Advanced Resource Recovery at the Primary Treatment Stage e-Showcase. Before we begin, I would like to quickly review a few logistics. During this webcast, while you cannot speak directly to the presenters, you will have an opportunity to submit questions by typing your specific question into the GoToWebinar pane that appears on the right-hand side of your computer screen. I will be accumulating these questions and will direct them to the presenters at the end. The PDF PowerPoint presentations are now available for downloading at WEF's website and are currently available in the Handouts pane of the GoToWebinar panel. This link was included in the GoToWebinar reminder email sent an hour before the webcast and will be included in the follow-up email sent 24 hours after the webcast has ended. We will be recording this e-Showcase. The recording link will be available on the webcast website 24 hours after the event has ended. PDH credits are not available for this event. Please note that today's event is a sponsored e-Showcase and does not necessarily reflect the views of the Water Environment Federation. If you have any additional questions after the webcast has ended, please email webcasts@wef.org. Today's speakers are Mark Stewart and Carlos Pellicer. Mark Stewart is a product manager at Veolia Water Technologies office in Cary, North Carolina, and is responsible for managing sales, marketing, and product development activities for the Hydrotech filtration technology within the U.S. municipal water treatment market. Mark began working in the field of water treatment in 1999. In 2004, he joined Veolia as a project manager, and then moved into his current role in 2009. Carlos Pellicer is the process manager at the Veolia Water Technologies office in Sweden and is responsible for process validation and process development for Hydrotech products. Carlos holds a PhD in environmental engineering from the Technical University of Denmark and has been in his current role since October 2013. Mark, I'll hand it over to you.
Thank you so much, Stephen, and thank you all for joining us today. We're going to jump right in here, and we'll be speaking today on the benefits of advanced primary treatment, but I wanted to give just a quick background on basic reasons for primary treatment. And you can see here in this graphic highlighting the two main benefits or reasons for primary treatment, one being to reduce the load to secondary treatment. Biological treatment with aeration accounts for a very large percentage and perhaps the largest pull for electrical usage at a wastewater treatment plant. So reducing that load obviously will reduce our aeration costs and be a benefit to the client. In addition to that, and in particular for today's wastewater treatment plants with anaerobic digestion, we can gain an improved energy recovery by taking more carbon to the anaerobic digesters, converting that into biogas, which is then converted into energy. And both of these added up mean, of course, end savings for the customer. In a standard conventional plant, normally we would do this with conventional primary clarifiers, a large footprint device, large area, and large retention time. You would expect to achieve about 50% suspended solids reduction. And one of the side items that does occur with this large area and residence time is odors. And these devices can be expensive to cover and difficult at times to deal with the odors associated with that. So when we speak of advanced primary treatment, there are a number of technologies today that are considered advanced, but in today's talk we'll be focusing on the Hydrotech technology. This is a Veolia technology. It's been in development and being sold since the 1990s. So it's a very established technology, and specifically for primary treatment has been in use since the early 2000s. What are the characteristics of Hydrotech compared to conventional clarification? It's a very small footprint device, a fraction of the conventional clarifier, and we'll share that in more detail in just a few moments. In terms of performance, you can also achieve the 50% suspended solids reduction that you would get with a conventional clarifier, But in addition to that, you can actually, with chemical pretreatment, achieve greater than 90% suspended solids reduction. And an interesting aspect to this is that the removal, whether of TSS or total phosphorus, COD, these can be targeted using a chemical pretreatment scheme. These units are covered. They have a short residence time. The operation and maintenance is very easy and straightforward. As we talked about the side issue with the conventional clarifiers being the odors, here with this technology, the odors can be reduced and are much easier to control because of the covered nature of the units as well as the short residence time. So in today's talk, we're going to focus on 4 key areas of benefits with this technology. One being footprint, the next being performance, the third benefit topic being control, and the final one being the easy operation and maintenance associated with the technology. So we'll move first into the footprint aspect. And definitely compared to conventional clarifiers, the benefit is fairly straightforward and easy to see. A conventional clarifier would typically be designed at about 1 gallon per minute per square foot, or in metric about 2.5 cubic meters per hour per meter squared. And when we're speaking of area here, we're talking about footprint area. With the Hydrotech filters, you can actually design these up to about 16 gallons per minute per square foot, or about 40 cubic meters per hour per meter squared. So as you can see, a fraction of the footprint is used compared to conventional clarifiers for the Hydrotech technology. And I thought it'd be interesting to share a specific site reference here. A location in Stavanger, Norway. This is a plant designed with 500,000 population equivalent. The peak flow design is 65 million gallons per day, or just over 10,000 cubic meters per hour. And they see inlet TSS up to about 300 milligrams per liter. Beautiful location in Norway, as you can see here, but you'll also notice that it's quite mountainous. And this is one of the big challenges with this site, was when they were looking at this location for their primary treatment, they would be needing to put it into inside of a mountain, actually. This location is quite landlocked, and so the location of the primary treatment would be going inside of caverns. So the cost of installation was at a premium in order to locate the primary treatment within the mountain here at the site. The site looked at a number of technologies, both conventional as well as other types of advanced primary treatment technologies, and did select the Hydrotech filters. You can see here the location inside the cavern where the filters are installed. This has 20 of our drum filter units up and running here now for about a year or so. I believe the startup date was early last year, 2017, here in Stavanger, Norway. So that highlights the footprint advantage. And at this point, I'm going to turn the presentation over to my colleague Carlos, and he's going to be sharing about the aspects of performance.
Thank you very much, Mark, and thank you everyone for being there. I would like to invite you all to a trip around the world in order to showcase the performance of our machines when they are installed in a primary treatment line. But before we do that, I would like to introduce you to the different modes of operation for Hydrotech filters in primary wastewater treatment. You can choose to operate the unit in 3 different ways. You can decide not to use any chemicals. In that case, you will achieve an average removal of about 50% of TSS. If you add a bit of polymer upstream in a flocculation tank and you allow the flocks to get larger and stronger with that polymer, you will be able to boost the TSS removal up to 90%. if you further add some coagulant upstream the flocculation tank, you will not only be able to increase the removal by 5% in comparison to the previous case, but you will also be able to remove some phosphorus. So please let's start our trip in Sweden, home of Hydrotech. We performed some pilot tests in the Helunda wastewater treatment plant located in Malmö. We piloted with both disc filters and drum filters, with and without chemical addition. And here you can see the results. In blue and gray, you can see the performance of both disc and drum filter without chemicals. And as you can see, the lines, the dots, sorry, align quite well with the removals that I mentioned before. We were able to achieve more than 50% TSS removal in average. When we added a bit of polymer upstream of the disc or the drum filter, those removals, you can see them here in yellow and blue, got enhanced to 90% in average, as you can see in this graph. Here you can see another data set that confirms the data that the numbers that I have already presented and the data before. In blue, you can see again the removals that you are able to achieve without chemical addition. You can see that those removals were in average above 50%. When adding a bit of polymer, the removals got between 80 and 90% in average. In green, you are able to see the removals that we were able to achieve when both coagulant and polymer were added upstream of the filter. In that case, the removals of TSS were above 90% in average. And we were also able to remove phosphorus. This is not just something that we are saying ourselves, and it's something that we have tested ourselves. It's also something that has been verified. It has been validated. Hydrotech, it's the only primary treatment microscreen technology that it's in the ETV register for green technologies. The ETV register, it's basically a database of green technologies with different claims, and those claims must be validated by an independent ISO 17020 certified verification body. Here in these two tables, you can see the results from that verification, both without chemicals in the left and with polymer addition in the right. The results in terms of TSS removal are in the line of what I mentioned before. If you don't add any polymer upstream, we were able to achieve 51% TSS removal in average. By adding 2.4 milligrams of polymer per liter, we were able to achieve 76% TSS removal in average. You have to be aware that the removals can be enhanced if higher polymer doses are applied in the system. Please, let's continue our trip through Denmark. In the north of Copenhagen, we have the Mølleåværket wastewater treatment plants, where they have 4 primary clarifiers. You can see them down here highlighted in red. They had some issues with them and they needed some serious renovation. So the client selected Hydrotech in order to be able to perform primary treatment with chemical addition upstream, because they wanted to control the COD removal and release some of the primary clarifiers for water storage purposes. Here you can see how the final plant looks like. You can see that one of the clarifiers doesn't have a cover anymore. you can see 1, 2, 3, and 4 Hydrotech drum filters treating the whole flow. Here you can see them. You have to be aware that the client also wanted to have some flocculation upstream of the units in order to be able to control the COD extraction. And that flocculation basin, it's actually installed in 1/4 of the inlet works to the primary clarifiers. The other 3 clarifiers, as I mentioned before, now are empty and ready to be refurbished for storage uses. The plant is still under commissioning. It's able to treat 925 liters per second. And here you can see the effluent turbidities that have been recorded over the last 15 days. As you can see, the average turbidity out of the drum filters has been around 100 FNUs. The inlet to the plant, it's about 250 to 1000 milligrams suspended solids per liter. And the first results that we have analyzed in the lab suggests that the removals are about 70 to 90% in terms of TS. Let's continue our trip, and this is actually our last slide referring data. The trip continues in Sweden, central Sweden. The city of Avesta has a wastewater treatment plant called NES, which was started up in 2010. They have a drum filter and a 2-stage chemical precipitation system upstream in order to remove phosphorus. The highlight of this installation is that the treatment line is purely mechanical. There is no biological treatment. And here you can see how the filters were able to remove more than 85% of the TSS in average, and how the phosphorus out of the drum filters was always below 2 milligrams of phosphorus per liter, which is the target effluent demand for phosphorus in this part of Sweden. The concentrations in the inlet of the drum filter were as high as 11 milligrams of phosphorus per liter. Some of you may be thinking if all this chemical addition makes sense, and this slide is actually for you guys. This is a life cycle assessment conducted by an independent body in Germany, the Competence Center of Berlin. They benchmarked 3 different technologies in terms of cumulative energy demand and global warming potential. They benchmarked them both under the same conditions, meaning that all 3 plants were receiving this influent, and all 3 sets of technologies had to treat the water down to these target values in the effluent. Here you have the legend for the different factors contributing to both the global warming potential and the cumulative energy demand. And you can see here how the microscreen with chemical pretreatment upstream actually benchmarked better than the reference conventional activated sludge without primary treatment, both in terms of cumulative energy demand and global warming potential. This is all I had to tell you. I am open for questions later on. Now I hand over the presentation back to Mark.
Thank you so much, Carlos. And we're going to be moving now to the third topic for the benefits, and that's the aspect of control. And so I think a good key question to ask is, why would it be important to have any type of very detailed control on the carbon removal? So I just highlighted a few key things here. One would be to minimize aeration costs. As we said from the outset, that's definitely a big cost contributor at the wastewater treatment facility, perhaps the largest. But we've seen in our calculations that the chemical dosage costs associated with polymer addition upstream of the Hydrotech primary filters is actually quite a bit less than the savings that would be achieved from the reductions in aeration. In other words, it would be a benefit to the client, even though there may be some added cost for dosing the chemicals associated with the added removal. That added removal would result in a savings, a reduction in the aeration, and an overall savings to the client. Next, of course, would be to maximize the biofuel production. The more we can remove, the more we can send to the anaerobic digestion, and the more energy that we can produce out of that carbon. However, having said both of those two bullets, it's important to put those together with the third, which is to stabilize the carbon to nitrogen ratio. And here, when we talk about that, it may be helpful to think about an example. So you can see here an example where we've said an example wastewater treatment plant may have an influent total nitrogen of 35 milligrams per liter. And a desired carbon to nitrogen ratio is typically about 8:1 to achieve full denitrification using that incoming carbon. We'd like to eliminate the need. We don't want to remove so much carbon that then we have to have another source of carbon introduced prior to the biology. We don't want to have to add cost in later because we remove too much carbon. So if you look here at this graph, this is an example relationship here between COD and turbidity. And you can see it tracks fairly well. And if we said, well, we want 8:1 ratio of carbon to nitrogen, and if we have a nitrogen of 35 milligrams per liter, then that would mean that our carbon would be 280, 8 times 35. If we look at our relationship here, 280 would target about 45 turbidity as being our target after the primary treatment to be going into our biological system. All the remaining carbon that we would then be removing out could be used for the biofuel. So we've done this a number of times using a fairly straightforward PI or proportional integral controller, feedback control loop. This is not something new. It's about 100 years old. It's well-proven technology, well-proven algorithm to do this. You could also combine this, and we've combined it with feed-forward. Having combined feed-forward control with the PI feedback control, it's a bit more complex algorithm, but it does give a faster response. But we've actually seen with our application that this is probably a bit more complex than actually is needed, that the basic PI feedback control loop really achieves very good results. We've also seen that our effluent from the Hydrotech filters is not really sensitive to flow variations when using this type of control system. And I think a big part of that is the short retention times that we see, both, of course, in the unit itself, which has a very, very short retention time, as well as in the coagulation and flocculation stages that we have ahead of the filters. If coagulants used, typically we're talking a 2 to 3 minute retention time, and with the polymer stage, about the same. So if only polymer is used, you're only looking at a 2 to 3 minute retention time stage, and then even with a combined coagulant and polymer, a total of a few minutes to maybe perhaps a max of 10 minutes total retention time when those are added up. And how is this done? You can see here a little basic schematic. We would take a PLC, The feedback control would be taken from an analog measurement, for example, turbidity, feeding back to the PLC and controlling using the PI control algorithm, the chemical feed, polymer and or coagulant. And as I said a minute ago, to make this, you could add a feed forward, whether using flow, turbidity, feeding back to the PLC, you could add that aspect to even provide a faster response on the control. And I've got a couple of photos here to show both pilot setups that have been done as well as full scale. Okay, so here's a graph to show some of these results. Up at the top here, this black trend is the coagulant dose for this particular trial that was run. The blue is the polymer dose. So both those two are being controlled. The red is the inlet turbidity. You can see the variation here in the inlet turbidity. The green line trend at the bottom is the effluent turbidity. And then finally, the black lines are the set points that were used for this particular trial. And it can be seen that the response here is excellent on the set point. So even with the adjustments, the controller was able to operate the system and give good response to track those set points through those variations in the set point and get a good response on the outlet turbidity value. This next graph again shows the same thing here, the turbidity being red in, the outlet turbidity being green. The black bars here are the set points. You can see two set points in this particular case. And the polymer dosage here in dark blue. The light blue is flow and is interesting to look at because of the flow variation. So we said earlier that the results could be maintained without sensitivity to variations in flow. And so we saw that here with flow ranges of plus or minus 100% on the flow. We still were able to maintain very good effluent performance, consistent effluent turbidity value using this control scheme. A question that will often be asked is, it may be that you've demonstrated this in a short-term pilot of hours or days, but what about long-term? And so here we actually have data collected over about, as you can see here, 15 to 20 days runtime. And the controller is looking at the feed, it's a feedback, so it's looking at the effluent and really trying to eliminate that error, either plus or minus, by adjusting the chemical dose. So it is self-stabilizing around that desired set point. And as you can see here, was able for a good duration here, about 15, 17 days of operation, to maintain that, with the exception of this one location here where we ran out of polymer. And that is difficult to maintain the set point when we did not have the chemical addition, of course. But once we were able to correct that, which happened going into a weekend, once we were able to correct that, quickly saw that trend return and be able to hold that through the remainder of the study here, very close to around that target value that we had set of 50 turbidity. Now finally here with this set of data points, on this particular graph we have the turbidity in represented with the blue trend. The gray trend is representing the effluent turbidity, and the orange trend is the polymer dosage. Our target here set point was 50, and the average over this period of time, this gray trend, the average was just over 50. So we can see here that definitely this control scheme worked. Maintained the average throughout this time period of this trial at the 50 turbidity. On the left-hand side here, we have the actual dosage between 0 and 6 milligrams per liter for the polymer dosing. And it's interesting to note that with a feedback control, we're actually targeting and putting the correct amount for the desired effluent set point. And the importance of that is that while other systems perhaps would use just incoming flow and set a milligram per liter based on the incoming flow rate, this method actually targets the effluent value and doses according to that feedback. So for example, we can see down here, even though the influent turbidity has some variation, you can see that the polymer dosage actually has quite a bit degree more variation in order to maintain that effluent, meaning that although there may not be as much variation seen in the influent, that it is seen in this control system that there is a need for the effluent to have this dosage optimized and varying in order to maintain the effluent target. And we actually saw with this facility that they were seeing periods of time where they had reject water streams from their centrifuge coming in and out at particular times. So that would not have necessarily been picked up at the inlet measurement point, whether of flow or turbidity, but could be seen at the effluent and impacting the effluent. And so the polymer dosage there being tied to that was an important aspect to maintain that effluent target control. So now moving from the control aspect, we'll pick up our final benefit topic, which is easy operation and maintenance. And we'll just highlight that in terms of the actual inspection tasks, access, the technology is very simple and straightforward. The background for the Hydrotech technology is for the aquaculture industry. And in that industry, anyone that's a fish farmer wants to spend most of their time where they are getting their livelihood, which is the fish. And so the thought process has always been to try to minimize this technology. It's a wastewater treatment device in those aquaculture plants. And so from the founding principles of the technology were to try to make it as simple to operate and maintain as possible. And that's been maintained even for our applications here in the municipal and industrial environments. You can see access to the filter media is very quick and simple, easy to see by accessing the covers, easy to replace as needed. And I think it's also important to note that the durability of the technology is a premium. So the media, we have many sites operating at 10 plus years with original filtration media, even sites with over 15 years of original filtration media on their machine. So both it is convenient as well as durable, making operation and maintenance easy to do and easy to understand. And so that highlights our benefits we wanted to share with the Hydrotech primary filters. Benefits being footprint, much smaller than conventional filtration and smaller than even other advanced technologies on the market today. Performance, knowing what the performance can be achieved, knowing that it can be achieved consistently and being certified even by third-party organizations. The control aspects, being able to control the performance to dial that in for a plant-specific needs. And finally, easy operation and maintenance, something that's important to every person that's working in a wastewater treatment plant. Thank you so much for participating here, and we're ready now to take some questions.
All right, excellent. Thank you, Mark. So we have a few questions here. We'll have about 10 minutes to go through these. So I'm just going to start going down the list. In your advanced primary treatment, how can you recover TP for reuse?
Yeah, so I think what you're referring to there is related to recovering the phosphorus for example, beneficial application. Carlos, I don't know if you have comments here. I think if you're collecting at the primary
Yes.
stage, that would be going to anaerobic digestion. I'm not sure how simple that would be. Do you have a comment there, Carlos?
No, it would go through anaerobic digestion, and then part of the reject will come back to the inlet works. That fraction of the phosphorus coming back to the inlet works can easily be recovered with struvite-based approaches, I believe. But as you are totally right, Mark. The main purpose of this technology is to recover energy. The sludge is better if it goes to an anaerobic digester, and once it leaves the anaerobic digester, the only stream through which you can actually recover phosphorus, it's the reject coming out from the centrifuge. We have also been involved in research projects in Finland where our partners have developed ways to recover phosphorus from our sludge, but that sludge is actually tertiary sludge, it's not primary. I don't really know how those results would extrapolate here, where the sludge it's quite different from what they have tested.
Okay, thank you. All right. How are filtered solids managed or removed from media?
Yeah, that's a very good question, and we can direct you to some videos that can be accessed as well for operations. But to try to explain it as simple as possible, the water flows to the inside of these machines. They're circular, round, cylindrical drums where the water flows inside, and on the outside of these drums is the filtration media. It's a filter cloth, and the water has to pass through the cloth to go downstream. So the particles then are captured on the inside surface then within the drum of the cloth media. By doing this, then the cloth can be rotated once it has collected a certain amount of solids. Then periodically we will clean those solids and remove them by washing them and cleaning them with a directed nozzle spray. And we will have a tray that collects then the washed solids that come off the media, collects those rejected solids, and takes them out of the unit. And we'd be glad to reference you to some videos that can be seen on our website for how that takes place.
All right, excellent, thank you. For your removal rates shown as a part of performance, what are the corresponding polymer and chemical dosages? Does dosage vary with influent TSS concentration?
Yes, that actually depends on the amount of TSS that you want to remove. That's what we were trying to highlight before, that our approach is fully flexible. The amount of TSS COD extracted from the wastewater can be easily controlled by adjusting the polymer dose into the process. The less polymer that you add, the less extraction that you get, the less energy that you can recover afterwards.
Okay, thank you. All right. Let's see. Can this system be applied to raw wastewater with no screens and grit removal system?
Well, I'll jump in there. I'd say that it's going to depend, I guess, on the quality of the water that's coming to us, and or I should say maybe the characteristics of the water. The filters will act as screening, of course, and so it will depend somewhat on the degree of the solids that are coming in, as well as the degree of grit. I will say that it will be more of a challenge to operate, and so there may be some conservativeness that would need to be implemented into the design. But I'd say it's possible, but we would need to know more. Carlos, would you agree with that, or have any other thoughts to that question?
Yes, I fully agree. You have to bear in mind that these filters were designed originally for the aquaculture industry. I don't know if you have visited many of these sites, but it's frequent to see food pellets that have not been eaten by by the fish growing in these facilities. Our panels have a patented technology in order to ease the removal of large solids. And when I say large solids, I would say solids which can be up to half of an inch. So as far as you don't get an alligator into your drum filter, I guess that that you are good.
Okay. Have you looked at using this technology in wet weather applications, that is, as an auxiliary treatment during peak flows?
Yeah, I'd say that it's definitely something we've looked at, and we actually have a site that was used for wet weather treatment in Denmark. Perhaps, Carlos, can you provide a little bit more detail on that facility that was used?
Yes, that's basically a facility which is built to treat wet weather flows. Actually, wet weather events are very sensitive in the Copenhagen area because there is actually people bathing in the harbor. So the municipality selected our technology together with some core screening and some UV downstream in order to be able to reduce the risk, the healthy hazards in the harbor after wet weather events.
All right, great. I think maybe we have time for one or maybe two more questions. What is the typical reject solids concentration? Does reject solids stream require further thickening for feeding to anaerobic digestion?
So I will defer to Carlos for some details on that. Go ahead, Carlos.
The solids out of our units are above 1%, no matter what you do upstream. When you add some polymer upstream of the drum filters, we can achieve, let's say, 3% up to 4%. It may not be enough for some digesters, but you have to take into account that you can take, when you have a facility with 20 filters, it may be a lot easier to collect the sludge from all the filters, thicken them up to the right quality that you require in your digester, and then put the thickened sludge in with the right quality in your digester. We don't have any thickening step built in our machines in order to enhance, in order to have a more simple unit to maintain.
Okay, thank you very much. I think that's all the time we have today. I want to thank Mark and Carlos for presenting and providing us with this information. I'd like to thank the attendees for coming and listening in, especially anybody that submitted questions. We will work with Mark and Carlos to follow up with anyone whose question didn't get answered. And I'd just like to remind everyone that we will have an email going out tomorrow to everyone that will include the presentation handouts, as well as a link to the recording for anybody that may have missed it or anybody that you may want to share it with. So on behalf of Wes, thank you everybody for coming, and we look forward to seeing you again. Thanks. Bye.